I was looking on the internet to try to find problems that involved circles and triangles, and I stumbled across this problem. And when I opened it up and looked at it, I said, "Oh, holy guacamole! I mean, uh, this thing is really confusing. It's uh, really a difficult problem to just figure out what the question means. But I've decided to look at it and see if I can solve it. Because certainly we should have covered the tools in the class right now. So let's look at this and see if we can figure it out. Um, First of all, we're given three circles here. We're given a circle O, which is the circle centered right here, has diameter AB, and we're given that CB is tangent to the circle O. So what that means is that we can count on this angle right here being a right angle. So this is a right angle right here, this line. We're given that CA meets circle O at D. This is CA, and it meets this circle O at D. And the circle of diameter AD. So this circle meets AB at E. So that also tells us that both of these circles go through this point D right here. And we know that both of these circles go through this point E right here. Okay? Is a circle diameter AE meets AC at F. So this circle right here meets this line AC here. And we're given that AD is equal to A, and we're given that DC is equal to B. Okay, so let's see. Let's look at this point here again. We have circle of diameter AD. This one meets this line there. We have a circle of diameter AE. So we're told, yes, we're told that both of these circles go through here. And they draw this line here, which is EF. Notice that, so what do we have? We have AFE is a circle that's inscribed in this semicircle right here. So we know that a circle inscribed in a semicircle gives us a right angle. So we know that this is a right angle right here. Okay. So far we have two right angles. Now let's see what we have to prove here. We have to prove that x is equal to this thing right in here. Wow. What really throws me a little bit here is we have this radical square root of AB. I wonder where that comes from. And notice that we have this set up. We have x equals a times this thing divided by that. That tells me we're working with some kind of a ratio here. That we could also write this as x times AB equal to this thing. So my guess is that we pull this out by looking at similar triangles or some other similar figures. This almost surely is a problem where we have to add some lines. So let's look at adding some lines here. In particular, let me draw the line that goes from point B on that circle to point D on that circle right here. So this now is we have the circle, we have the triangle, I mean, ADB. That's also inscribed in a semicircle. So that tells me that this angle here must be a right angle. This angle here must be a right angle. Okay, let's draw some more lines. Let's draw this line right here that goes from this point on the orange circle down to this point on the orange circle right there. Again, that circle is inscribed, that triangle is here, here, and here. That's also inscribed in the semicircle. So that triangle is, so this angle right in here is going to be a right angle. And, okay, we have this, we've drawn this. See if we want to draw any more lines in here. I think that might be it. Let's see where this takes us. Okay, notice that we can also draw this triangle. I don't know if that will buy us anything. Let me draw that one right here. Okay, I have the line. I'm going to drop the perpendicular from this down to here. My guess is I won't need that for anything, but we'll see. Okay, I have, and because I drew this to be a perpendicular, I know this must be a right angle. Okay, so these three lines right here are all perpendicular to the same line, which is the radius of this purple circle. So those three lines must be parallel. So that's telling us that this triangle and this triangle and this triangle must all be similar triangles. Similarly, this line and this line are both perpendicular to this line. So these lines must be parallel. That tells me that this triangle and this triangle must be similar triangles. Okay, and so let's see where this all takes us. To begin with, I want to look at this triangle here and this triangle here. No, let's see. I want to look at this triangle here and this triangle here. Why? Because this triangle has a side that's equal to A, and this triangle is a side that's equal to A, and they both have this side DB in common. So let's look at this triangle right here has diagonal AD, which is also equal to A. So we look at the ratio of this when I look at this triangle, this isn't a diagonal, it's a side. So this triangle has the side A and a side DB. Okay, that's what I'm going to look at. I'm going to look at the ratio of this side to this side is A over DB. So I have A over DB. Okay, so that's this side to this side. Now, on this triangle, the long side is DB, and the short side is B. So this ratio, A to DB, is the same thing as DB is to DC. So this equals DB to DC, and DC is B. So this gives me A times B, AB is equal to DB squared. So that might be where that square root of AB comes from. Okay, so we looked at two similar triangles to get that. Let me tell you again what they are. It's this one, and we're looking in this one. Okay, in this triangle, we look at the long side over the short side, and it has to equal the long side over the short side on that triangle. So that's where that comes from. Now let's look at two other similar triangles. I want to look at the big similar triangle here, because that diagonal and that one is equal to a plus b. So because I'm looking at a way to get this a plus b right here. So this, let's look at this triangle right here, and we'll say that triangle is going to be similar to this triangle right here. Okay, so that's so we have this diagonal is a plus b, that's the long diagonal, and this diagonal is a. So on one side we're going to get a plus b to a. But what I'm going to, but I want to get the dB into the equation, and dB isn't one of the sides of this triangle, and it's not one of the sides it's not one of the sides of the big triangle, although it is one of the sides of this triangle right in here. See, is that what I want to do? I want to get A, B, and A on one side. A is a side, A plus B. Okay, I want to look at this triangle, this big one, but I don't want to look at this triangle here. What I want to do is look at this triangle. A plus B to A. Okay. See how confusing this is? I'm going to look at this triangle and this triangle, which is originally what I said I wanted to look at. So I have this diagonal as A plus B, and I have this diagonal as A. But what I'm going to look at are these altitudes in the two triangles. This is an altitude in the big triangle, and this is an altitude in the smaller triangle. So the ratio of the altitudes in the big triangle is equal to dB, and this triangle, the altitude is equal to x. Okay, so see what I've done here. I've used something that I discussed in an earlier video. I said that when we're looking at similar triangles, the similarity ratio applies not only to the sides, but to other one-dimensional features in the triangle. So I'm looking at the big triangle, and I'm getting the ratio by taking the diagonal of the big triangle and comparing it to the diagonal of the smaller triangle. So that gives me A plus B divided by A. But I'm not looking at the other second features I'm looking at does not include the sides of the big and the smaller triangle, but rather includes this altitude. So this altitude compared to this altitude, that's where I get the dB over x. So I have this is my similarity ratio that I'm using. So now let me take these two equations and solve them. This equation right here tells me that the square root of AB is equal to dB. So now I can rewrite this thing as A plus B divided by A equals the square root of AB divided by x. Okay, if this equals that, then I can cross multiply here, and I get x times A plus B is equal to A times the square root of AB. Now I divide both sides by A plus B, and I get x is equal to A square root of AB divided by A plus B, which is what I originally had to prove right here. So I proved that, and I proved it using similar triangles, and I took what was probably somewhat of a shortcut in that solution by remembering something I talked about in a previous video, and that's when we have similar triangles, that it's the similarity ratio is true not only of the sides of the similar triangles, but of other geometric features in the similar triangles. And in this case, I took my two geometric features to be the altitudes. In other words, I took this altitude, the ratio of this altitude right here, and this altitude right here, and said that ratio has to be the same as the ratio of the two diagonals. So this is the diagonal of the short one, and this right here is the diagonal of the longer triangle. So that's how I did that. And it was a relatively few number of steps, but boy, does that problem throw you for a loop when you first look at it. So till next time.